Okay. So yesterday last class we discussed short circuit computations using Thevenin theorem. Okay. But this is a very lengthy method. Therefore, we need to find out a method where some algorithm can be used to compute the three-phase short circuit current. That is the objective. What is the objective? Objective is to find out the three-phase symmetrical short circuit current. Okay. The objective is to find the three-phase symmetrical short circuit current on a single phase basis. And we can do that by finding out the Thevenin equivalent of the circuit, PSOC by RTH. So before to do this short circuit computation on a systematic basis, we need to use a network model. Consider part of a Zbus system where the short circuit is applied at bus Q. So what we need, just mention pre-fault voltage, pre-fault bus voltages. Point 1 is pre-fault bus voltages. So that is a n vector of bus voltages. Okay, so we have a n-dimensional vector of bus voltages because it's a large system. Last class we saw a two bus system, but when we do a practical power system, it is an n bus system. Okay, large number of buses. Upon zeroing on all active sources and after regulating the generator and transformers lines forced by their internal impedances, we arrive at the Thevenin network. So point 2 is the Thevenin network, and the effect of fault is represented by that Thevenin EMF. Okay. In this network, the bus voltage represents the states caused by the fault, which are summarized in n-dimensional voltage vector. Okay. So this n-dimensional voltage vector is the pre-fault voltage. Okay. Now, the Thevenin theorem states, then you write this equation, equation 3. The Thevenin theorem states the bus voltage during fault is equal to the pre-fault bus voltage plus the fault current. Okay. So, this is the voltage across the fault resistance. Vf is the voltage across the fault resistance. If it is a solid fault, that is 0. Vf is 0 if it is a solid fault. And therefore, this n bus system can be represented by an n cross n Z bus matrix. Okay. Therefore, we can represent the faulted network by means of the final equation, where V bus is equal to Z bus into I bus. I bus is the fault current, V bus is the pre-fault voltage, and Z bus is the impedance, equivalent impedance of the faulted network. Now, if you find out this Z bus, then we can easily compute the fault current. Okay, you do not go for Thevenin equivalent. Okay, so this is the principle behind fault computation on a systematic basis. This is the principle. Okay. Now, this shows in detail how it looks like. Okay. So the pre-fault voltage is before the fault, given by a voltage vector. Write down the voltage vector. This is the pre-fault voltage vector, and this is the Thevenin voltage across the faulted terminals. Okay. The bus current is injected at one bus only, that is at bus Q of the amount minus IM, because there is only one bus where the fault has occurred. That's what we are assuming, one fault at a time. And therefore, the fault current is given by this, where this is the faulted location. Okay. And this Thevenin voltage is given by Z bus into IL. Last class we did this manually. We found out the Thevenin equivalent impedance. Okay. Okay. And hence the total voltage at the faulted bus is given by this equation. We will see one example. So these are the principles behind fault obtained on a systematic basis. Right now, these three equations. V bus, the Thevenin voltage, and the fault current. Okay, and we are taking one fault at a time. Therefore, the fault current is injected at that point only, the faulted bus. Next. So this is the next question. Question number 4.1.4. See the question. Consider the V bus system shown in figure 4.3, which is here. This is from the Elder book. Draw this paper. Draw this paper. So we can find the detailed solution here in the other book. This is that diagram. Okay. So here, see what we discussed. We need Z bus for computation of the fault current. But Z bus, that is one algorithm in which we are going to develop Z bus. In this case, we will do that by matrix inversion. Okay. So we are formatting the Y bus first. We are formatting the Y bus first. So you know how to find the Y bus. So these two elements, right? So this is the impedance J10. What is J.1? What will be the admittance? Y12. 1 by right? That is equal to minus J. There. Okay. And you know this is minus y12 and this is also minus y12. That is the principle of formation of y bus. Right. That's why this is J10. Okay. Similarly, all are same. Therefore, and this is y23 minus y23 and this is minus y23. Okay. And what about this? So you know that this is capital Y11. Capital Y11 is equal to 1 by J.05. That means Y10 plus Y13 plus Y12. So 1 by J.5, 1 by J.1 and 1 by J.12. Why 1 by? Because these are impedance values. So we need to convert that to admittance values. Therefore, capital Y11 is this one. So if you add this up, this becomes this. Similarly, you can find out the impedance or the diagonal elements here. So write down this Y bus and no need to write. This is the Y bus. Our purpose is not Y bus here. We are not doing load flow. We are doing fault calculation. For that we need Z bus. Okay. So what is Z bus? Z bus is equal to 1 by Y bus. Okay. this metric is also you know, you have to find the determinant, 1 divided by determinant, then you find the cofactors. Okay. Anyway, so you can do that. So Zbus becomes this by inversion. So in this case, Zbus becomes this by inversion. Okay. Fine. What is the first part? For systematic fault computation, the first part is finding the Zbus. Here in this example, we are doing that by inverting the y-bus. Next, we will see how to do that systematically using an algorithm that you are doing it in your lab. We will see the question. What is asked? It says, consider the 3-bus system shown in figure 4.3 where 100 and 200 MVA generators are feeding. There are two generators feeding. You might have drawn the network via step of transformers power into the buses 1 2 respectively. In the 3 transmission lines are assumed of equal impedance J 0.20 on 100 MVA base. It is, see here it is given J 0.20 on 100 MVA base, but we have used J 0.1. Why? Why? What is it? Question is the line impedance is J 2.0 per unit. The J 0.2 per unit. How many units to J 0.1?
100 MB.
Yes. So that was, this is given 100 MVA base. But since here the highest generator is 200 MVA, so we have to convert that to 200 MVA base. So what it asks, what is generally asked in short circuit studies? It says find the short circuit capacity at all the 3 buses. All the 3 buses, how much is the maximum value of the fault current, and hence the corresponding fault MVA. Then after that, find all the short circuit currents and bus voltages following a solid symmetrical short circuit at bus 3. So once you know the capacity, find out this. All 3 pre-fault voltages assume to have 1 per unit magnitude. Pre-fault voltage take always 1 per unit. Okay. And generator reactances including transformer 0.3 per unit. Okay. Okay. So this is the Zbus. So how to find out the short circuit capacity? See here. So for bus 1, the fault current is pre-fault voltage by the Z value. Okay. So pre-fault voltage is 1, Z value is 0.073. Similarly, for bus 2 it is the diagonal element. For bus 3 it is this diagonal element. Okay. So we are going to use the diagonal elements of the Zbus matrix to find out the fault level at different buses. Now this is the current value. This is the current value. Now since the voltage is given to be 1 per unit, we can consider this to also be a short circuit capacity value. Hello. Now suppose we have taken, I think this will be, this is on, this is 685 MVA. Okay. So we have to find out, see the base MVA here. Okay, we'll see. What is the base MVA here? What is the base MVA here? Multiply करो. Okay. So this question has 50 MVA base. This question has 50 MVA base, and therefore these are the short circuit capacity of at different buses. So that's the first part of the answer. Then it says, what is the next question? Next question says, this one we have answered. Short circuit capacity of all the buses. Find all the short circuit and bus voltages for a solid symmetrical short circuit on bus 3. So there will be a fault on bus 3, but we want to know the current at different buses. So how to do that? We have to use the same equation that we wrote from the very first principles. So you see here. So here we have computed these voltages, fault voltages, okay, using the equation. That equation you have written for V1F. You have written the equations, right? V1F, what equation you have written? VF. VF is equal to V0 plus fault voltage. Okay. Which is equal to, this V0 is 1. It is given, na? Take all the voltages to be 1 per unit before fault. So that's why V0 is 1 in all the cases. V3 is always 0 because V3 is 0. Why V3 is 0? No, V3 is 0 is. V3 is 0. Okay. So first we compute the voltages at different buses. Then using voltage divider rule, we find out these voltages, and finally the current will be computed based on, for example, I want to is V1 minus V2 divided by the impedance of the transmission line. Okay. So these are the fault current at different buses. Next is, this is the assignment. This assignment is actually the next question in the record. Okay. The next question using the same concept. So you can try this. Okay. This assignment is assignment 4.4.2. This one. The same method will be applied here. Figure 4.9. Okay. Try. This one is assignment. Next. So far this is one part where we discussed that the Zbus will be computed by inverting the voltages. So we started with the equation to compute the short circuit current. Okay, that is first we compute the voltage using VF is equal to V0 plus VF. V0 plus VF. That is the first step. Okay, and that we demonstrated using this example. But here we have inverted the Y bus to get the Z bus. But this is not the way it is done. So what we do? We use Zbus. Okay. We have found Zbus by inverting Y bus here. In this question, we have found Zbus by inverting Y bus. For large system, it is arguably because of inverting a very large matrix that is computationally very costly. Okay. Using direct assembly methods, so if we use direct assembly methods, the Zbus is built by adding one network branch at a time until the total network is assembled. So this is the basic equation that is used. Okay. Here Ij is equal to Vj divided by Ij, provided all the remaining currents are zero. Now this is the actual algorithm. So did you see that program that I have uploaded? You get for Zbus program. Did you see that? Okay. So what is Zbus algorithm? So Zbus building algorithm is a step-by-step programmable technique which proceeds branch by branch. Consider that Zbus has been formulated up to a certain stage. Okay. So Zbus means branch by branch we are adding. Okay, suppose we are in a stage and we are adding a new branch. So what you do? So we have got the following equations. Type 1 modification. Okay. Jet is added to form a new bus to the reference bus. Type 2 modification, type 3 and type 4. Okay. So these are the modifications. Now, if this modification occurs, how you are going to change the Z bus? This is the formula. Okay. Similarly, for type 2, this is the formula. Type 3, this is the formula. Type 4, this is the formula. Okay. Now, at your level, at undergraduate level, nobody expect you to remember this algorithm. You should know how to. You should know that there are some steps, that is type 1, type 2, type 3 and type 4 modifications which can be used for building a Z bus, and for that the program is already given. Okay. Now, how this is implemented? This is one example. Okay. Suppose this is a network. Okay. So for this network, build Z bus using the Z bus algorithm. So what are the steps? So these are the steps implementing these steps. Okay. Okay. So all the steps I have written here. So eventually the Z bus is configured with this. For this, since it's a 3-bus system, it's a 3x3 Z bus. It's not sparse. Y bus is sparse, but Z bus is not sparse. All the elements are somewhere. Okay. So now, in the exam, if the Z bus algorithm comes, nobody is going to ask you to implement Z bus algorithm, but you should know what is actually Z bus algorithm. So for that, just write down this slide. Okay. Stop.